Hi, STAT students. Welcome back for section 8.2a. We're going to do this in two parts. So we're going to talk about a z-test. So we've talked about quite a few things so far, our hypotheses and our critical values, and now we're going to put everything together and we're going to actually perform a hypothesis test. So first, let's talk about our z-test for a mean. There are things that are going to sound very familiar from chapter 7. The first thing about a z-test is you do know your population standard deviation. You know sigma. That was an important thing that we had to know in order to know what kind of critical value back in the last chapter when we were doing our confidence intervals. Typically, we're also going to double check to make sure that our n is greater than or equal to 30. Remember, sigma is the number one thing we look for. Sample size is next. And important, we've seen the z formula before. Our z is equal to x bar minus mu all over sigma divided by the square root of n. We use that in that central limit theorem, right? That's why we're using x bar minus mu, not just x, a data value. So quick thing over here on this right-hand side, x bar, everybody knows that is a sample mean. Everybody knows mu. Population mean, we really need to do a symbol quiz. Everybody knows sigma, population standard deviation, and last but not least, n is our sample size. So all of these things we've been doing, there is nothing new here. We have calculated the z value, our critical value, before and talked about all of these things. So there's 5 steps for hypothesis testing. We have covered 4 of them up till now. So step 1, and I'm going to have you do these in 5 steps. So I'm going to have you write down step 1, state your H sub O and your H sub 1 and identify the claim. We have not done that, but we're going to just have to read and find it. We did this in section 8.1a. Step 2, we're going to find our critical value. That was what we did in the last section. That was in 8.1b. Right? We talked about jumping into the z table. We need to know if it's one-tailed or two-tailed. So is it alpha or alpha over 2? All those kinds of things. Step 3, compute the test statistic. In this particular case, remember it's going to be z, because this section is called z-test for a mean. Now, I just gave you that formula just now, like 2 seconds ago in section 8.2b, or sorry, 8.2a, and we've also done that back in that central limit theorem section. Step 4, we have not done yet. We haven't talked about it all, but we have taken all the steps. We have to make a decision based on our critical or non-critical region. Are we going to reject or not reject the null hypothesis? Remember, that's always the decision. So in step 4, you're going to write down step 4, reject H sub O, or step 4 will be do not reject H sub O. Those are your 2 options. We don't do anything with H sub 1 until step 5, where we summarize the results. Summarizing the results was in section 8.1b, and I believe it's also on page 425 in your book. That's where we say, oh, there is not enough evidence to support blah, blah, blah. So, and yes, you have to summarize every single time. That's part of the whole hypothesis testing process. So here are our 5 steps. We're going to stick with them very faithfully. So let's do a couple examples just so that we can get through these problems so that you've got something to look at. So example 8.4, z-test. So a researcher believes that the mean age of medical doctors in a large hospital system is older than the average age of doctors in the US, which is 46. Assume the population standard deviation is 4.2 years. A random sample of 30 doctors from the system is selected, and the mean age of the sample is 48.6. Test the claim at alpha equals 0.05. There is a lot of information in there. Let's start just by seeing what we've got. So let's state the null and alternative hypothesis. Let's draw the picture so that we can see what we're looking for finding the critical value. So I typed out step 1 through 5 here. You're welcome. I want you to write that out every single time. 1, it makes it easier for me to see what you're doing, and 2, it makes it easier for you to see what you've already got and to have a process as you go through this. So H sub O and H sub 1. Right? What does it say? A researcher believes that the mean age of medical doctors in a large hospital system is older than the average age of 46. There it is. There's everything we need. So H sub O is always an equality, right? So we're going to say that mu is equal to 46. The researcher believes that the average age is older than that. So older would be greater than 46, and this is my claim, right? That's what the researcher is believing, claiming, saying, trying to answer. There is our information. So what this is going to look like, if I draw it over here, is here's my mean of 46, and this researcher believes that it is older. Therefore, we know when we find the critical value that this is going to be a right-tailed test, right? Because we shaded to the right because we believe that they're greater than. So this is right-tailed. In order to figure out our CV, we need to know alpha. Well, it says test the claim at alpha equals 0.05. Now, since it's right-tailed, since it's one-tailed, do we have to split this alpha up? We don't, right? All of that data is over here just on this right side. 0.05 alpha equals 0.05. So that's right-tailed, though. Remember, our CV is going to be a positive number. So technically, I should go into my table and I should look up all of this, which is 0.95. 95%, or I look up 0.05 and I put a positive value on that critical value, or maybe you even have this written down somewhere. I believe that for that 0.05, my critical value is 1.65, and it's got to be positive because it's right-tailed. So this number right here is 1.65. This diagram may seem like nothing, but it's going to come in handy as we finish this up. So now I'm going to compute my test statistic. There's a lot of information up in that reading part in order to compute our test statistic. Our test statistic is that Z formula. Z is equal to x bar minus mu all over sigma divided by the square root of n. So let's jot down. Notice I'm calling my step 2 a critical value. I'm not calling it Z. I know it's on my Z table, but it's my critical value that's telling me should I reject or not reject. So let's see. It looks like assume the population standard deviation, sigma, is 4.2 years. A random sample of 30 doctors. There's N. The mean age of the sample is X bar 48.6. I think that's everything we need, right? So I'm going to plug everything in there. So 48.6 minus the mu, go back to your H sub O. Mu equals 46. It tells us that right there. All over sigma 4.2 over the square root of 30. Get your calculators out. Hopefully you've got them. Remember, when we are finding Z values, we go to 2 numbers after the decimal, right? Because that's what our Z table tells us we need. We don't look up anything else. I think this comes out to a pretty big Z value. Have you had an opportunity to do this calculation? I ended up with, hit pause and calculate, make sure you got a 3.39. So here's what we're doing. Here's what our decision is. Our picture comes back to us. So I know that everything from 1.65, my critical value, to the right is shaded. 3.39 would fall somewhere out here, right? That's going to fall in that critical region. Well, if it's in the critical, aka rejection region, we reject. So reject H sub O. The reason is my test statistic, Z, well, right, now write Z. Z is in the critical region. You don't have to write that down. I just want you to know why I am saying it's a reject. This Z value is in my shaded region because everything from 1.65 to the right is shaded. Now, if I got 1.64, that would be like right here, right? That would not be in the shaded region, so I would not reject H sub O. All right, so we've got everything we need. Step 5 is the fun written part. I'm also an ELA teacher. So we reject H sub O, and our claim is H sub 1. So I go back to that little chart, either on page 425 or in my last set of notes. If I reject H sub O and H sub 1 is my claim, that means I'm going to say something like, there is not enough evidence to support the claim. This is the exhausting part. There's not enough evidence to support. It has to be legible, the claim. Some people don't do this, and what's the point of doing a hypothesis test if you're not summing it all up? That, what is the claim? The claim is that the average age is greater than 46. The average doctor age is greater than 46. That's it, right? There wasn't enough evidence to support the claim. The claim was this one, so we can just put that right in there. You have officially done your first hypothesis test. We took all kinds of bits and pieces and calculations and put them all together. Hopefully nothing seems super brand new because we've done a lot of this stuff in isolation. Now we group it all together. All right, so let's do one more. So Z-test, using the critical value method. The average 1-year-old is 29 inches tall. A random sample of 31-year-olds in a large daycare franchise resulted in the following sample of heights. Can it be concluded that the average height differs from 29 inches at a significance level of 0.05? Assume that sigma equals 2.61. Well, let me just give you a piece of information that might be helpful. We know this, right? Sigma. If I give you a bunch of pieces of data and like in the last problem, we said, oh, well, we calculated that the average age was 48.6. Wouldn't we need to calculate the average height? So let me just tell you, in case you need some time to get your TI-84 or add them all up and divide by our n, our x bar is equal to 29.45. I'll just give you that bit of information. I think that's everything that we need in order to do this. So let's go through our same 5 steps. All right, state the null and the alternative hypotheses and state the claim, or identify the claim. So H sub O, H sub 1. Well, H sub O is always our equality, right? The average 1-year-old is 29 inches tall. That is our H sub O. Mu, our average, is equal to 29. A random sample resulted in the following. Can it be concluded that the average height differs from 29 inches? There is our H sub 1, our alternate hypothesis. If it differs, it doesn't say that it's greater than or less than 29 inches, right? It just says it differs. So this is one of these guys. We're just saying, can we conclude that it is different from 29 inches? Here is our claim. Most of the time H sub 1 is our claim, but you do have to watch. It's not an always definite thing. So let's see, if I were to draw this picture just so that we can see what it looks like so we can get our critical value. Here's my mu at 29 inches because that's my average. And it's just saying that it's differing. So will it be one-tailed or two-tailed? If it's not equal, right, it could be larger or it could be smaller. So if we're going to find our critical value, our first thing is that we need to know our alpha significance level of 0.05. But use your common sense. Because it's two-tailed, that 0.05 is split evenly between both of those. So our alpha over 2 is what we've got to use. If it's two-tailed, we always divide by 2. So we'll have an alpha over 2 of 0.025 or 0.0250, which means we've got a positive and a negative critical value, that dividing line between the shaded and the not shaded. So this is 0.25 and this is 0.25. And we're going to jump into our Z table. We're going to look up 0.25 and we're going to find that our critical value must be positive and negative. And when I looked it up, I found a 1.96 on either side. So this is negative 1.96 and positive 1.96. So those 1.96s are our dividing line between our shaded and our unshaded. So now if we can figure out our test statistic, we can figure out, does it land in the middle where there's no shading or does it land in one of the ends? So we're comparing our test statistic to that critical value shaded regions. So our test statistic, remember, is Z equals, let's see, so it's x bar minus mu over sigma divided by the square root of n. So let's see, we should have all this information up here, right? I told you x bar, 29.45. Our sigma was 2.61. What else do we need? A random sample of 30. So there's our n, and we know our mu because mu is always in the null hypothesis. So I can figure out where I can see these things. So x bar was 29.45 minus my mu, which is 29, so it's a little bit bigger for this particular sample. 2.61 is my standard deviation divided by the square root of my sample size. It is just a coincidence that I used 30 on two different problems. It won't always be 30. Remember, we like our sample size to be 30 or higher, but I look first to see if I know my sigma. If I had 25, it wouldn't be the end of the world because I do know my population standard deviation. Take a quick pause here. Make sure that you calculate out the same thing as me. You will get a positive and negative critical value, but we only get one test statistic. I believe when I checked this, I got a 0.94 for my test statistic. So I know that my cutoff point for the shaded regions is negative and positive 1.96. 0.94 probably falls right about here. 0.94. That is in the non-shaded region. If my test statistic falls in the non-rejection region, am I going to reject or not reject the null hypothesis? That's a do not reject, right? So I just write out do not reject H sub O. That's all you have to say for step 4. So step 5, we go to that table and we say, oh, well, we didn't reject H sub O, and H sub 1, my alternate hypothesis, was my claim. So where do I find that on my little table? And what does it tell me to say? I believe it's going to tell you to say there is not enough evidence to, hold on, is that what it's going to say? It's going to say we did not reject H sub O. There is not enough evidence to support the claim. Did I have the last one wrong? There is not enough evidence to support the claim. And what is the claim? That the average age differs from 29 inches, because that's the claim, right? That the average age differs from 29 inches. Now I got to go back and look at that last problem and make sure that I did that right. If I rejected the H sub O in my claim, there is enough evidence to support the claim. Oh, I did that right. Right? There is enough evidence. What was I thinking to support the claim? All right. Sorry about that. Take that not right out of there. So on this one, we didn't reject it. We liked this one, and our claim was the other. So there's not enough evidence to support the claim. We like H sub O. All right, so quick, remember, when your test statistics is in your critical shaded region, so when what you calculate falls in the critical region, reject H sub O. That means that your difference between X bar and mu is not likely due to chance. It's a sampling error or something else. When your test statistic falls in the non-critical, non-shaded region, there it is, do not reject H sub O. That means your difference between X bar and mu is likely due to chance. It's small enough that it didn't really make that much of a difference. That is it for section 8.2a. Sorry about that one extra word that messed me up in that first example, but you've got the idea. Don't forget to go back to all those different bits and pieces. Have a great day.